Hello everyone, welcome back to Electronics 1. Here we are at lecture 6, and today we're going to talk about the operational amplifier. Some of you, depending on the path you took to get to this course, may have taken classes in the past where you've talked about operational amplifiers, but we have a variety of backgrounds, so we're going to talk about them again here for a few classes. If you have not already discovered, there are a selection of slides up on D2L. If I can go to those, that are I inherited from one of my previous colleagues here that taught electronics at UMB. They're very good slides and very complementary to the topics we're discussing, so please find those in D2L under additional resources or something like that. So just a bit of background on op-amps. Op-amp was originally developed for commercial use in 1951 using vacuum tubes. The idea was originally conceived even before that, 1941. But this is an example of one of the first commercially available op-amps, very large and much different than what we see today. In 1963, the first monolithic op-amp, and what we mean by monolithic is a device that's produced on a single die of silicon, that material that electronic components and integrated circuits are produced on since back in these early days in the 60s. And we'll talk more about silicon a bit later in the class. So a guy known as Bob Whittler back in 1963 was working at Fairchild Semiconductor and came up with initially the ECE3111 op-amp, which eventually was succeeded by the ECE3111, which was then followed by the ECE3111, which was really the first op-amp that became very popular, and many textbooks and resources that introduce op-amps still tend to use the ECE3111 as kind of the introductory op-amp device that they refer to. In fact, here's a look at the internal components that make up the ECE3111 op-amp, a series of transistors, resistors, capacitors, diodes. This device, which is a very simple op-amp in today's world, is made up of 22 transistors. So even in the early days, it was a fairly complex device, and they're much more complex than this now. Okay, so let's talk about some of the defining characteristics of an operational amplifier, or what we'll generally just abbreviate as op-amp. So an operational amplifier has 5 main terminals, and those terminals consist of 2 inputs, 1 output, and 2 power supply connections. Okay, and we can show our typical op-amp in a circuit diagram, is shown like this, and we'll, sometimes, often when we're showing in a diagram, and most of what I'll do in class, I won't in fact show the power supply terminals that may be called VCC plus and often just called VCC and maybe VEE, depending on the technology used to design the op-amp. But again, this is the positive power supply, and this is the negative power supply. And again, these pins are often excluded in diagrams, but it's important that we don't forget that they're there. And I can, again, referring back to those slides, I can pull in a nice graphic of a op-amp, but this op-amp goes further to show the internal components that we model in an op-amp. What's great about an op-amp, and it's one of the few devices that you tend to deal with that behaves very close and approximates very closely an ideal device, and that's an ideal voltage amplifier. Okay, so although we show an input resistance and an output resistance, the input resistance of an op-amp is in fact very high, and the output resistance is generally quite low. So again, for that reason, it approximates an ideal voltage amplifier. Where our input approaches infinity and where our output approaches zero. Another aspect of the op-amp that makes it operate ideally and makes some of the analysis quite simple, as we'll see here soon, is the voltage gain of the op-amp. That term that's shown here as AOL is extremely high. And it's on the order of typically maybe 10 to the 5 volts per volt to 10 to the 6 volts per volt. And for that reason, we often consider it to be infinite. Another aspect of the gain that's key to an op-amp and very characteristic of an op-amp is the gain is differential. So what that means is that the output of the op-amp depends on the difference between the two input terminals. Okay, and this has many benefits and allows us to configure the device in a variety of configurations. These two input terminals are referred to as the non-inverting and inverting inputs. So if we go back up to the diagram here for a second, maybe it's easier for me to just switch slides. If we look at the input terminals here, we see that they're labeled on the on that triangular block that's so characteristic means of representing an op-amp. They're labeled with a positive and negative sign, but we don't talk about them as being a positive and negative input. They're the terminal labeled with the positive symbol is referred to as a non-inverting input. That labeled with the negative symbol is referred to as the inverting input. Okay, so these are referred to as non-inverting and inverting terminals or inputs. Okay, let's talk about these characteristics and the consequences of some of these characteristics that we just got done talking about. Okay, so the consequences of the op-amps, and these are ideal characteristics, and we'll see that these aren't the op-amp doesn't truly have infinite input impedance and zero output impedance and infinite gain, but we often treat them in that as those ideal conditions, and it again will make our circuit analysis techniques much simpler. Okay, so the input resistance being infinite, the consequences of this are that if there's no input resistance, or sorry, if the input resistance is infinite, that means that no current enters the inputs. Okay, and further to that, thinking about our discussion about amplifier models here just a lecture or two ago, this also means that no attenuation occurs at the input when we connect a device that has some source impedance other than zero, which is really any device is going to have some source resistance. But now it doesn't matter because with no current flowing, we'll get no voltage divider effect. Okay. Okay, the other ideal parameter is that the output resistance is zero. So what are the consequences of this? Well, if we look back at our diagram, we see that the output voltage, sorry, fix up my V here, is a function of this gain that we said is very high, the open loop gain as we're going to call it, times the differential voltage. Let me just go back up to the diagram and highlight those. All right, the differential gain voltage being that voltage difference between the non-inverting and inverting terminal. So our voltage that's generated by the amplifier is the open loop gain times that voltage. Now if we're saying that this resistance the output out is zero, then this voltage that appears at the output here, this V out, is going to be exactly equal to this open loop voltage times the differential voltage, the gain times the differential voltage that's applied to the input. Okay, so let's define some of these things. VOL is what we call our open loop gain. VD is the differential input voltage. And again, if this case is true, then we have no attenuation at the output. There's no, again, voltage divider effect like we saw when we're looking at our amplifier models. Another aspect of the differential input that you may not immediately think about, if the differential input means that the differential voltage, which is that voltage that is amplified, which is the difference between the voltage applied to the non-inverting terminal minus the voltage that's applied to the inverting terminal, the impact of this input being differential means that the common mode gain is 0. Okay, what do we mean by common mode gain? Well, if I use a little diagram here, so let me draw an op-amp. Again, I'll draw it as a 3-terminal device and exclude the power supply connection. So if this is my op-amp, if I have a situation where I have the same signal applied to both inputs, and call this signal the common mode signal, because it's common to both inputs, with if everything operates ideally here, and this differential voltage that exists here is the difference between the voltage at the positive terminal and the negative terminal, while the difference in this case is 0, so my output voltage should be 0, meaning that my common mode gain referred to as ACM is 0. Okay, this has very beneficial implications in environments where there is noise, maybe electromagnetic interference that may be, both inputs may be subjected to. The nature of this differential input and this common mode gain that's 0 will eliminate the noise from the desired signal. Okay. The other thing that we stated up above is that the open loop gain, I'll just define it here again using its the name that we generally give to, or the symbol that we usually use to define open loop gain. That's A subscript OL. Okay, so this is open loop gain. Open loop gain we often assume to be infinite. And what are the consequences of that? The consequences of an infinite open loop gain is that there's no voltage difference at the input. So this one's a little bit harder to wrap your head around. So let's look at it just algebraically. We've said that the output voltage is equal to my open loop gain times my differential voltage, and we know that the differential voltage is equal to the voltage at the the voltage at the non-inverting terminal minus the voltage at the inverting terminal. So if this use a different color here, if this open loop value is infinite and I desire an output that's finite, that's not infinite, right? I want an output from my amplifier other than infinity. Infinity is not very useful for me. I don't want an infinite voltage value, and in fact we're going to see that the voltages applied by the power supply limit how high the output voltage can go, and we'll talk about that later. Well, if this needs to be finite and this is infinite, well, that means that the difference between the non-inverting and inverting terminal must be 0 in order to get a finite output. Okay, so taking that a little bit further, if the difference between these is 0, well, it must mean that the voltage, let me show these like this, the voltage at each of those terminals must be equal. Okay, so this again being defining the voltage at the non-inverting terminal and the subscript, the negative subscript, is the defining the voltage at the inverting terminal. Okay, so we'll leave off here today, but just something to think about going forward is it doesn't seem all that useful to have a gain that's infinite, right? That doesn't give us much control over the amplification, and we know that the open loop gain is not in fact infinite. And back here we said that the open loop gain is in fact on the order of 100,000 to a million volts per volt, but again that seems excessive, but even if it isn't excessive, even if that is the kind of gain that maybe you want, one of the issues with the open loop gain is that it's highly variable and we can't rely on it being a known fixed value. So the next class we're going to investigate how we can use negative feedback to put to allow us to gain control over the magnitude of the gain of our operational amplifier circuit.